what we got is we got this basis of scalar integral. So we now have the method to compute all these coefficients here analytically, and these coefficients multiply some scalar functions, as they are called, and these are all known in the literature, and they're available computer libraries where you can download them and use them directly in your calculation. So yesterday when I was talking about this, I realized that there was one slide in my talk missing, so I'll go to that one now, and that was about divergences. Because these integrals here, they are not all finite. Some of them are divergent. They both have UV divergences and also infrared divergences. These coefficients here, they're all finite. You can easily show that they are, and also this R term here, they're all finite. You don't contain any poles in 1 over epsilon if you use epsilon as a dimensional regulator. So we can still use the same methods to get these coefficients, and then all the dependence on the regulator is in these scalar integrals here, and also in the UV renormalization. You should not forget that after we've done this decomposition, we still have to renormalize our theory to get finite results. So once you solve the system and we do UV renormalization, we have the full dependence on the finite piece of the integral, but also in the soft and collinear divergences, which we know should cancel against the soft and collinear divergences in the real mission corrections, according to the Kalen theory. So we get this virtual, which then is the finite part, and we have the 1 over epsilon pole, so we can also compute this B1 coefficient and the 1 over epsilon squared, which is B2 coefficient. We don't get higher powers in epsilon here because we're just doing the one-loop calculation, and therefore we only get 1 over epsilon and 1 over epsilon squared poles, because we can only have at most one soft or one soft and one collinear. One soft or one collinear, or both of them together. So there's no higher divergences here. So yesterday I also told you then that this method, this Pasolini-Veltman reduction method, is very, very nice because it can be straightforwardly generalized to any one-loop integral, and in principle we can automate it in this way. But there was a clear disadvantage that even for relatively simple processes, the number of terms that you have to keep track of and you have to compute just grows enormously, and you have to really do hard work to simplify your final result and get something that you can compile on a computer and compute very special. And also, it does only work when the integrals are really known analytically. That is, you have an analytic expression for the things that you try to simplify. If you just have it numerically, like in the MGraph code, there's no way you can do this in this way. So then I stopped here with this next leading order revolution. So 0, 1, 2, and 0, 1, and 2 jets took a long time to go from 0 to 1 jets, and an even longer time to go to 2 jets. And then something in between here happened that made 3 jets and 4 jets seem relatively easy. And then what has happened there in between is something that I will discuss in this lecture this morning. So there came some new techniques, new loop techniques, and there's basically 3 different ones of them, and I will only go into one of them a bit more detail later on. So the first one is this generalized unitarity. You use the unitarity of your matrix elements to compute directly the coefficients of your integrals. There's the integrand reduction method, which is, for example, in Cuttles and Samurai, and there's improvements in this Pasolini-Veltman tensor reduction technique, for example, by Denner and Dietmeier, and also in an automated code which is called Column. So only about the second one is what we'll discuss in a bit more detail during the lecture. So there are other techniques, for example, the generalized unitarity technique, which I will not cover during my lecture. So if you're interested in in other methods to compute these loop integrals, I suggest you to look at these papers here and try to understand what is going on. So I'll only go in a bit more detail about this integrand reduction. yesterday is that any one-loop integral can be decomposed in terms of these coefficients times scalar integrals. Right? So the idea is that we should find these coefficients as efficiently as possible, analytically or even numerically, right? Because in the end what we want to get is a distribution, a plot, a prediction, a number. So it doesn't mind if we compute them analytically or numerically. So we might as well just do it numerically. If it's numerically easier, you just do it numerically. So in this new technique, which is this integrand reduction technique called OPP method, after Papadopoulos and Peter Howard developed this only a few years ago, is to do this reduction at the level of the integrants instead of the integrals. So this method has been automated in a program called CutTools, which you can just download from the website of Peter Howard. And what this program does for you is that if you give it a function, then it's one loop function, it finds you these coefficients in an automated way. So and this program is that what we're using together with the MGraph code to compute these one loop diagrams. So I'll go a bit more detail about how this method works. So yesterday we did this decomposition at the level of the integrals. So we had our integral, and we had this L mu in the numerator, and we decomposed this in terms of this P mu and Q mu because we know that that's what the only possible functional form of the final result could be. So we got a system, linear system in that way. Now, so if you would know a similar, so this is at the level of the integrals, if you would know a similar relation at the level of the integrand itself, we can get these coefficients in a more efficient way. And that is what this OPP reduction does. So the decomposition is in fact the same, except that some contributions might integrate to zero. So let me show you, one example which makes this clear as what I just wrote here on my slide. So consider, for example, that we want to get this box coefficient. So at the level of the integral is just given by the box coefficient times the box integral, which is just this coefficient times this integral. Right? So we want to find these coefficients. Of course, this is equal to the line here because this coefficient is independent of the loop momentum. Right? So this is trivial. However, we can always add a function here which depends on the loop momentum as long as this integral over this function is still the variable here is equal to 0. Right, you can so the same coefficients which enter here at the integrand level are also there at the integral level, also there at the integrand level, except that there are some spurious terms as they are called. And of course the same is true for the C, the B, and the A coefficients. So these are called spurious terms. So we have to deal with them. So let's go back to our one loop integral here. So this was the definition of. So we have this numerator function, and then we have this denominators here, and which were defined as the loop momentum plus the p squared minus the mass of the external line, and this p squared was just the sum of all the previous external momentum going into the loop. So in this case, P1 is equal to K1, while here P2 is just K1 plus K2 plus K3 because all these three momenta came here, and P3 is then the sum of all these 6 momenta here. Right? So now what we can write now is that this numerator function here is actually given by this equation here. This is the core of the OPP reduction, so I want to spend a bit of time in explaining what is here. So here you see the same coefficients, B, C, D, and A, as we had before. And again, here by this whole list. So then there are only 4 D's left, right? There's only 4 D's left. And these are exactly these 4 D's which were here. Right? So what I've written here, this first line, is exactly the same as this line here for a given I0 to I3. Right? Does it make sense? So this notation is kind of a complicated thing, but we'll see that this works out rather easily later on. So just because I multiply here by all these except the 4 ones that I'm interested in, I get exactly this coefficients times the box. Similarly, for this triangles here, I multiply this by all possible D's except 3 of them, and these 3 are exactly the triangle integral corresponding to the coefficient that I was looking for here. And again, we have this possible extra spurious term that vanishes if we do this integral here. Right? And then similarly for the D, I just take all the D's here except 2 of them. So in this ratio here, all the D's drop out except the I0 and the I1. There's 2 of them here. So that is exactly the box coefficient here. And then we have again these possible spurious terms which integrate over 0. And similarly for the A0 and then similarly for the rational part. So this is just another way of doing the same decomposition as we had here, which was at the level of the integrals. We do the same decomposition here at the level of the integrand, where these coefficients are the same coefficients as in the previous slide. Does this make sense? Yes? Very good. Questions on this? Who does not really understand what I'm doing here? There must be somebody. There's always something. There's nothing to be afraid of, because it's a complicated way of writing something which is maybe not so trivial. Okay. So what do we gain, right? Because we write the same thing in a slightly different way, and so what is the gain? That should be your question. Why did we do this? Why do we want to do this? So now, what we can do now is we can choose specific values for this loop momentum L, and then we end up with a system of linear equations that we can solve. So we can just pick values of L. L depends on L is in the numerator. It's in this coefficient, the spurious coefficient here, and it is in this D's here, and also in, of course, the numerator. Right. But we can choose specific values of L, and then we get a system of equations. Right? And because these coefficients D do not depend on L, we should be able to solve the system numerically. So that's the idea. So what we do is we set up this system straightforwardly by sampling this numerator function numerically for various values of the loop momentum L. And by choosing this L smartly, the system can be greatly reduced. In particular, if you choose L to be a complex form factor, this works rather well. So we choose the values of L. We get a system of equations here. So we get we choose the value of L here. So this becomes just a number. This becomes also just numbers, and accept that these coefficients, D, C, D, and A, we should solve. Of course, this means so we have to know some information about these spurious terms to be able to work this properly. However, these spurious terms, the functional form of these spurious terms is actually known. There's a paper by Aguilar and Vidal in 2004 that exactly show you how the dependence of what the dependence on the loop momentum of these spurious terms is. This is a simple one. So what I decided to do is not show you at all how how this is done, because if you want to know, it's hard work and you have to look at this paper, and it's a bit of a complicated thing. So I can only show you one example basically, which is kind of easy. And that is if you have a box coefficient of rank 1, then the numerator of this spurious term can only be basically this one, because it's the only thing that integrates to 0 in this way. So this is, for example, how the dependence of this spurious term is when it's just one momentum there.
But we are doing d-dimension, not 4-dimension, right?
Yeah, I'll come back to this. Good question. So this functional form of all these spurious terms is known. So that of course, otherwise we couldn't really solve this system. But because this is known, functional form of these d's is known, we can get these coefficients by just choosing values of L and setting up this system of equations. And then if we choose L smartly, we greatly reduce the system. So, for example, one of the choices of L, which is very smart, is to choose L such that all, for example, all these denominators are equal to 0. Now, you can only find the solution of this system if you choose L to be a complex vector. And in fact, there are two solutions because this is some quadratic equation. So you can show that there are always two complex solutions to this equation here. So why is this a very smart choice? This is a very smart choice because if you look at all these products here, so this is a product of all possible d's except one. One is not included, which means that if I take all possible d's, there's definitely going to be a d0 or a d1 somewhere, which means that this thing is 0. So this whole line does not contribute to my system of equations at the set. Similarly, for the bubbles, there's two of them, which I don't include. So there's always two of those still there, which means that also this thing is 0. Similarly, for the triangles, I choose 3 of them, which I include all these except 3 of them. So also there must be one of those still in this line. So only the first line actually will contribute if I set all these, when I choose my L such that all these d's are 0. Right? So I get a very simple equation between n of L and my coefficient d if I choose my L such that this is true. Right? So all these terms here drop out, and I'm only left with this line here. So my numerator, if I choose L such, is this d coefficients times this product of these, where then this I is not equal to this 0, 1, 2, 3 here. Right? Because only this term survives. Now, given that there are two solutions, and I know my functional form of d here, I can directly write my d coefficient to the one that I'm looking for. Right? I'm looking for these d coefficients as this sum of these two terms here. So this is how I get, for example, my first d coefficient. And now I can choose other values of L, which set other 4 denominators to 0, and I get other d coefficients. And in this way, you can get all my d coefficients by choosing L such that still all the time 4 of these are not always the same 4, but still 4 of these, all these possible d's are here are 0, because then all the time this part does not contribute, and I'm only left with this first line, which gives me a very simple system of linear equations that I can easily solve directly by just inverting this way. Right. So once I get all my d coefficients, I can go to the next step, and that is by choosing another values of L, the momentum, setting up the system of linear equations, inverting it, getting directly the results. Right. So then we go on iteratively, and we get the B coefficients and then also the A coefficients. Right. Does this make sense? Right? I think it should. So in practice, for each phase space point that we want to compute a virtual, we have to solve a system of equations, right? Because our value of L, for which this is true, depends on the phase space point, because it's D depend on the phase space point. It's D, let's see, sorry. Because these D's were, depend on L, but they also depend on P, the external momentum. So for each value of P, for each possible phase space point, I have to solve the system of equations. And then by choosing special values of this loop momentum, my system greatly reduces. As I showed you, you can choose this such that some of these denominators are 0. My system just shrinks. And therefore, even though we have to do this phase space point by phase space point, this is still an efficient way of doing our decomposition. Also, we can do this decomposition at the level of the amplitude, or for a single diagram, or somewhere anything in between. So this numerator function, this n of L, can be defined by a given diagram, or it can be the whole amplitude at once, where you have all possible denominators in there, all possible inverse propagators in the denominator. So in MGraph, we decompose at the level of the diagrams. So we do this decomposition diagram per diagram. So we compute one diagram, we do the decomposition for that particular phase space point. We go to the next diagram, we do the decomposition for that phase space point. We get this coefficient, we multiply everything out. But we are now working on improvements in this consideration, and we think by grouping certain classes of diagrams together, we might actually get a reduction. So, because we have to do this reduction for every given phase space point, we have to compute the diagrams more than once for every phase space point, because we change the momentum of the loop when we sample the diagram, so we have to recompute the diagram all over again. And this is of order 50 times or so for 2 to 3 passes. So it seems like a lot, but in practice it's not so much. 50 is quite reasonable. So this is still kind of a fast method. So, for example, one little example that is usually shown in these when we do this decomposition is, suppose you want to do this integral here, which is a 7-point integral. It's a very complicated thing to do, and if you want to do this with Vassarine-Veltman reduction, it takes a long time because we have to decompose it to tadpoles, bubbles, triangles, and box integrals. So this is so from 7 points to 4.6 is complicated. So in this example, we have the numerator equal to 1, and this again these are defined as usual. So and to get, for example, this box coefficients is very easy. So let's just find the first box coefficients. So we take 2 solutions of this equation, like we always do for the box coefficients, and then we can directly find the box coefficients in this way. So it's really so for one given phase space point, it's really just a computation which is very straightforward. To find these 2 solutions is very easy, and then also to get these coefficients is just by computing these 2 numerator functions here. Average. So this is how it works. Questions so far? So, this is just the first box coefficients, and then we have to compute the other ones as well. So this will take, it's a bit more time than just the first one, but this is the idea. Yes, Carl. L is a 4 factor, yes.
And is that the complex?
Complex, yes. So this L is not, so even in this integral you say L should be real, but to solve the system, to set up a system of equations, you don't care what this L exactly is. You just want to choose values of L and such that this system reduces, and therefore you can get easier your coefficients. Because the final result will be independent of L. So it doesn't really matter how we do this, what kind of values of L we choose, except that smart values, just reduces the system considerably. So that they're complex or not doesn't really make anything more complicated. Doesn't make it more complicated.
Is it always guaranteed that there is a single one pair of solution for F plus this equation?
Yes, as long as the external momenta are not collinear or exactly the same or something, then this is always guaranteed that you find two of these solutions.
Coefficients are all real.
No, the coefficients don't
The
be.
so
So these are complex numbers. I mean, these depend on the numerator of propagators, whether it's can be an I, D slash, or whatever. So they are really complex. Yes.
So you solve.
Sorry.
Sorry. You solve four quadratic equations with four complex numbers. L square and L plus L square in terms of L0, L1, L2, L3.
Yes. Again, I quickly mentioned yesterday this Van Vermaaseren basis for loop momentum. I didn't really go into this because this is some complicated. But he uses basis. This is a trivial, almost trivial equation. Right? It becomes very easy. So I do, yeah.
See that the
Yes.
we can solve it.
Yes. It doesn't matter. So in my example here, we have some of them on shell, but others are off shell. So so it can be anything. It can be massless, massive, off shell, on shell. It doesn't make any difference.
Probably even if the mass scale is conscious, probably we can solve it, right?
So I already got a question about this, about we are working in D dimensions, and so far I choose L to be four-dimensional. I treated everything kind of four-dimensional. So there are actually some complications when you go to D dimensions. So I was very sloppy in what I was doing. I was just treating everything four-dimensional. But that is not correct, because then you don't get, in fact, the correct answer. So in general, when we do this loop calculations, we always choose the external momentum polarization factors in four dimensions, and only the loop momentum in D dimensions. Because that is the most easy way of doing these loop calculations. And you can do this because external momenta are living in our four-dimensional world, and then only the things that diverge, where the divergences are coming from the loop integrals, those you treat in D dimensions. So my notation is such that things living in D dimensions have a bar above them. So D dimensionals have a bar. Four-dimensional objects has nothing, and the epsilon dimensional part has this tilde. So a D-dimensional, four-dimensional part plus its epsilon dimensional part. Right? So in fact, we should compute this integral here. So the numerator should depend on, there should be a bar too, sorry. I already see my first mistake. So the numerator should depend on the four-dimensional part and the epsilon dimensional part. And then the denominator should also be in D dimensions. So in D dimensions we have that L is in D dimensions, P is still in four dimensions, and then mass is also just a mass. So by using the fact that a four-dimensional object times an epsilon dimensional object is 0, we can write this as in this way. So our D-dimensional object is our squared, is our four-dimensional object squared, plus this epsilon dimensional object squared. Because a D-dimensional object dotted with a four-dimensional object is just the four-dimensional part. So L squared, L bar squared is L squared plus L tilde. So D bar squared is just D squared. Sorry, D bar is just D plus L tilde squared. Right? So the implications for this is in fact that when we do this decomposition to find these coefficients, all these scalar integrals are in fact should be in D dimensions. So there's always should be bars everywhere. Right. But the coefficients don't change because the coefficients don't depend on the momentum itself. So the main difference is in fact in this rational part. This is where this R contribution is not. So far I kind of ignored this contribution here, except when we did this Basel development contribution I quickly mentioned. But today so far I ignored this R contribution. So this is how we get this R contribution. If you just use everything four-dimensional, you will still get all these coefficients, but you're missing this piece here. So the main difference is that we get this rational term system called the R, and we saw this already in yesterday's lesson about decomposition. So in this OPP method that I described, this reduction at the integrand level, they are generally split into two contributions called R1 and R2. Okay, you can always split something up. But the split is actually useful because you can design that they are coming from different parts of the calculation. R1 is coming from somewhere else than R2. However, both still have their origin in this D-dimensional thing, so in the part of the UV part of the model. So I'll show you both of them separately where they are coming from. So the R1 is canonically called as the origin in the denominators of the propagators in the loop. we go from a 4-dimensional object to a d-dimensional object, we can write this d-dimensional object as the 4-dimensional object again, with a small correction, 1 minus this epsilon dimensional part of the loop momentum over the 4-dimensional part. So because we choose our epsilon dimension small, also this loop momentum squared is kind of small. Right? It has to be small because it's just a small extra extension of our dimension. So this is small. So this is kind of an exact equation. So of course, this propagator structure is known because we're doing exactly this decomposition in the scalar integrals. So for a given scalar integral, of course, we know exactly how this functional form of this L tilde squareds are. So you can include this in the OPP reduction. Yes?
In the right-hand side of the first equation, the first one of E should be 1 over dI.
Oh, sorry, yes, it should be a dI.
And then, in order to make it exact, I think the second one should be L tilde squared over dI bar. And probably you ignore the higher order in each.
So I ignore the higher order in epsilon.
Yeah.
So this
equation should come in the next step because it's not really equal.
I agree, but L tilde
Yeah,
squared.
I agree.
Yeah, so it should be order epsilon. That's also the reason why I can ignore the bar here.
Yeah, I understand, but otherwise this equation is difficult to understand.
Oh, okay, yes.
I mean, it's just an identity, it's trivial.
Yes.
Yeah. And then you approach it.
Okay, yeah. Yeah, I agree. The I is really missing. Yes. But the first scalar integral, of course, we know exactly what our D's are and D bars are. So we know exactly the difference between doing it in 4 dimensions and doing it in D dimensions. Right. So we can, in our reduction, we can get this contribution kind of for free, because the only places where they enter is that we should add now and then some factors of pi squared over 2. Because if you're looking at these scalar integrals here, we can get this L squared contribution, and they are given in this way. So these R1 contributions are not really any complication to compute. The other contribution of the rational part, what is called R2, so the other place where this epsilon dimension might enter is in the numerator itself. Right? So in the denominator, we have explicitly now solved all this epsilon dependence. But in the numerator itself, there might also be some loop momentum there, and therefore also there's some epsilon dependent part in the numerator itself in general. So if we just have 1 power of L in the numerator, it's not going to be any problem, because 1 power of L is always contracted with a 4-dimensional object with some external momentum, and the d-dimensional object multiplied by a 4-dimensional object is just a 4-dimensional object. The epsilon dependent part drops out. However, there might also be cases where there's actually 2 powers of L in the numerator, and if they are contracted, if there are 2 powers which are contracted, then we get so if there's just 1, I showed you, then it's just a 4-dimensional object. If there are 2, we get the 4-dimensional object plus, again, this epsilon dependent part. So this is what we should include, right? So if we have an L squared in the numerator, we should include an extra contribution there. However, if we do something numerically, it's very difficult to find out if we have an L squared there. We have to do, normally we do analytically, we do a Clifford algebra to get the spinor indices, we have to do all these gamma matrix multiplications. And And then maybe in the end we find somewhere an L squared. It's not clear that if we have two powers of the loop momentum that we always get an L squared dependence there. It might be that they contracted in different ways only with four-dimensional objects, and then we don't get this dependence. So this is very difficult to do numerically, and we cannot do this by just giving a numerator to a numerical number to the Cuddles program, which does the reduction for us. There's no way that this program can find out where this possible L squared dependence is. Right? So this dependence might be very much hidden, so we have to do something else. However, given that they are from ultraviolet origin, there's only a limited number of places where they can occur. So they can only occur in objects that might be ultraviolet divergent. So if you just do dimensional counting, it might only be in loop calculations which have 1, 2, 3, or 4 external particles, not more, because if you have more, then the integral is always ultraviolet finite, and then therefore we cannot get a contribution from these L squared terms. So there's only a limited set of loops in a given theory that can give a contribution to this numerator. So there's a limited set of things where it might come from. And in the standard model, they have all been identified exactly. And in fact, they can be treated as extra Feynman rules, in the sense that if you have a loop diagram, which might give contribution, for example, that should roll down. For example, if we have a diagram like this, this has a possible UV divergence. And in fact, if you work it all out, you can find out what the epsilon dependence is in such a vertex. So in such a diagram. So what you can do is you can write an effective vertex. Which computes only this little epsilon, this L tilde squared contribution to this diagram. So we get, if you do the decomposition, for this diagram in the OPP reduction, you get a whole diagram contribution, except for this little contribution coming from the L tilde squared dependence in the numerator. So we can add an effective coupling here, which we compute once and for all for the standard model. So we say always that you just include an extra Feynman rule to a theory that computes the little L tilde squared dependence of the numerator here. That's how we do this.
So the bottom vertex has a 1 epsilon 4 plus
So these are always finite. So these are coming from contributions. These are given by these kind of integrals here. So if you have this L tilde dependence in the numerator, so this is a triangle integral, so we have kind of this thing. So this effective vertex will be proportional to pi squared over 2.
And at this level, you keep this right as 1 epsilon 4 diagonal. You just keep it.
So this is finite. scalar integrals. These coefficients are finite, so we just get these coefficients, and then later on, when we get the coefficients, we can multiply them with the scalar integrals, where we can take the finite part, or we can take, if you want to compute the poles, we take coefficients in front of the poles. So, yeah. That's right.
By the way, this L values are more complex number, right? L bar.
This is all complex because we choose.
So what is the measure? So it's
So in fact, well,
when you say L tilde scale, is it L tilde L tilde star or complex congruity? L times L complex congruity?
no, it's
Not
it's
positive Latin?
no.
It's not.
So well, this we treat analytically, this L tilde squared, because of course, if we give a numerical value to our loop momentum, we just give it in 4 dimensions. So that's why we need this special treatment of our d-dimensional part, right? So this is we treat analytically and we solve this way. But if you have another L squared somewhere, it's not the complex conjugation. It's really, thing squared. So this is how we get. So with these effective kind of vertices and final rules, we get our 2. So I give you 2 examples of, for example, for a bubble, we get a correction like this. Like this one here, which is, which has some dependence. And then for this example that we showed here, we get something like this. And all of these contributions are known in the standard model. And because they are of UV origin, as I told you, they only come in this kind of propagator corrections, vertex corrections, and then also in there's 4 interaction corrections. But no 5 or 6 or higher point interaction, because these integrals are always UV finite, and therefore they cannot give you any contribution from this L tilde square. So, however, they are still model dependent. So for the standard model, they have all been identified. But for beyond the standard model things, they are not known. And the idea is that we actually use the Feynman rule package that Benjamin introduced in his lectures to maybe compute them mathematically for any given. But this is still kind of work in progress. We might have some ideas how to do it, but it's not. They even started already with computing of the UV counter terms in this way.
But in common, we have the algorithm for decision on heads. Now we know to transfer it from our heads to the code. That takes time.
Yes. So the idea is there, and it just has to be implemented. That's basically the same.
What is the lambda HP?
Yeah, good question. This lambda HP depends how you define your epsilon extension of your 4 dimensions. If you define it to be positive, I think it should be lambda is 1, and if you define it to be negative, lambda is 0, or the other way around. That might get confused. So what are the now the clear improvements over the old-fashioned Brazilian development approach? So as I showed you in Brazilian development, we can do this. We need analytic expressions, all intervals, and we can possibly automate it. But there are too many terms which are difficult to simplify. So we have it's money because we can automate all the stuff, but then it's kind of a sad story if you go to more complicated integrals. So this OpenP reduction reduces this system as the integral that I also showed you. And we can solve this system numerically. So we only need the numerical function of the numerator of the integral. And then we can set up a system of linear equations by choosing specific values of the loop momentum L. And of course, they depend on the kinematics of the event. So that's kind of good that we can do it just numerically. And we just need a numerical function, and we don't need any analytical expressions at this point. And then we can then choose L smartly so that these internal propagators goes on shell, which means internal propagators on shell means that these D's are 0, right? 1 over. So if a propagator on shell means that the denominator is 0. And then we get an enormous simplification of the resulting system, so that's also good. This reduction is implemented with cut-tools, which is publicly available. And so given given such a numerical function of the integral, cut-tools will do the work for us and compute for us all the coefficients from the scalar integrals and this R1 contributions to the rational part. So that's also good. So there's one sad thing here, and that is that there is still analytic information needed to compute this R2 term. So to do this, compute these effective vertices here. But the good thing there is that we compute them once and for all for any given model, and then we implement them in the computer code, and we can do any loop computation in that given physics model. So for the standard model, they're all there. For the standard model theories, Benjamin is working on it. So therefore, this is not really such a bad thing as it looks on first sight. So how did we implement this in MGraph? I think I have 5 more slides or so. So MGraph is very good at giving numerical expressions for matrix elements. That is the core of MGraph, right? It computes matrix elements, 3-level stuff, all numerically, and then that's it. So this is exactly what is needed by cut-tools, except that it's only 3-level. So how do we force MGraph to compute things loop diagrams? So that's what we call MATLOOP. Right? So and the idea is actually quite simple, and the idea is the following. So if you have this loop integral again, so what we do is if we cut this diagram open, so we just say, well, we remove this line here, or parts of it, and then we get 2 extra external lines. And then it becomes just a 3-level graph. Right? It's just you get 2 extra external particles, but in the end it becomes 3-level. And this is something MGraph can do very well, 3-level stuff. Right? So there's one complication again. Always there are complications. The complication is in this case that, well, we can cut this line here, we can cut a line here, or we can cut a line here. And all of them are the same loop diagram, while we give different 3-level diagrams. So if I cut this line here, I get this one. Right? And this is clearly a different 3-level diagram than this one. So we get many more contributions than we need if we just let MGraph generate all possible. We type in the Born process, and we get 2 extra final state particles, or external particles. We get many more diagrams than we need. So we have to build in a filtering algorithm to filter all of them out to just get only one loop diagram, even though there are 2 different 3-level structures contributing to it. So these things have all been implemented. So that is this what I mean here by so these are new features implemented in MGraph to do loop diagrams. So that's, for example, we need to recognize these loop topologies and filter all the diagrams that we don't need. And then there are various other things that we need to implement. But given that I'm running out of time, maybe we should not spend too much time on this. Except maybe this point here is that so when we compute these kind of 3-level diagrams, what cut-tools needs is just the numerator of these functions, not the denominator. So we just have to compute these diagrams without including the denominator. Also, if we compute the diagram which is cut open, we have to somehow glue it together again before giving it to cut. The real loop diagram is a closed loop. It's not something bridge is cut open. So if we do this, if we do, for example, this diagram here, which has these two extra gluons compared to the loop diagram itself, we somehow need to sum explicitly over these polarization vectors to get back again what is normally the propagator of a gluon in a loop. And then we need ghosts, of course, which are not needed at tree level. And then we also need this rational part R2, should be R2, sorry, and the UV normalization we should implement as well. So maybe I should stop here, and then I have time for questions still.
Well, any questions? Yeah, please. We have it difficult for there is. Yes.
Not yet. It's still, as I told you in the very first lecture, that there's still some restrictions on things we cannot do, and it doesn't give you any warning when you try to do it. We decided not to make it public yet because it's too dangerous to give it to everybody, and then they'll do their own calculations and don't realize that what they're doing is actually not right. I'm sure you're not one of them. There's always people who are doing it in this way. Just don't look at the manual. Just try to run. Yeah, so that's the main reason why it's not that done.
Yes.
So the gluon polarization in this method is D or 4?
So this is in. So we do everything in 4 dimensions in the end, right? Because we know the analytic structure of the denominator functions, and therefore we can compensate for the fact that we're treating everything in D dimensions. And we can also compensate for the fact that the numerator has to be computed in 4 dimensions by computing this R2 terms, by computing this effective vertices that is shown. So in practice, we do everything in 4 dimensions, and then compensate for the fact that we should have done it in D dimensions.
So if you want to do dimensional regularization, probably this remnant will contribute to R2. But if you do it in dimensional reduction regularization, there's nothing from this group propagation. Right? I think I want to start in one of these.
Oh yes, yeah, this is
Also minor.
yeah.
Depending on your.
It's yeah.
Okay. So any other questions?
Yes.
Choose your external element for dimension, each one for the dimension. And this choice should be related to the regularization scheme you use, and choose the other choices on the possibilities.
Yeah, so in principle you can, so the old-fashioned way of doing the conventional dimensional regularization is to choose everything in D dimensions. But that's not really needed because the only place where really divergences occur are in this loop integral. So it's okay to just keep everything in 4 dimensions because that's simpler to work with, and then only choose the loop momentum itself in D dimensions. So that's what is the more modern way of doing dimensional regularization. I think this is the most convenient way to do only this loop momentum in D dimensions and keeping everything else in 4. So there was, I showed you this little scheme dependence, which was this question about what are these lambda HV here. So this is where scheme dependence is. So you can choose a scheme. So this is the only place where scheme dependence happens. So I mean, in practice it doesn't make any difference what scheme you use because it's just small variation here. But that's it.
The scheme dependence will cancel when you do the migration of the coupling. So if you do the regularization parameter reduction, your coupling is also parameter reduction with normalized. And that scheme dependence will cancel standard and the scheme dependence of the renormalized. I think.
Yeah, together with the dependence in the real mission. So in the counter terms for the real mission, there's also dependence on the same kind of structure. So there's also a dependence there. So yeah, this it's not difficult to do this correctly. You should be careful. And you do it consistently over all your calculations. You just have to keep track of this.
The point is, you should break some symmetry, okay? Always regularization. Yeah. So if you want to keep supersymmetry, you should violate Lorentz symmetry, right? Because you should treat 4 dimensions and E minus 4 dimensions differently in dimension reduction. In this way, we can keep supersymmetry, okay? But if you want to keep 3-dimensional Lorentz symmetry, then actually you should do dimension regularization. And then, of course, supersymmetry is broken. So actually, in order to preserve supersymmetry, you should need extra counterterm, yeah, to restore supersymmetry after regularization. Okay? So at the very end, in physics, it's okay. But the regularization is not, the point is, a good example is this chiral symmetry. So there is no symmetry, no regularization, which is possible to preserve both gauge invariance and the chiral symmetry or supersymmetry. Yeah, that there is a very deep reason for this. So you choose your convenient regularization, and then if you know that this regularization violates some symmetry, then if you want to impose this symmetry in renormalizable theory, then you need to add a counterterm to restore this symmetry. That's a very standard method. Yeah, you do it always. Yeah. So it's just unfortunate that we don't have a, or fortunate because we have some things of Pluto